So, what if I told you there's this hidden language that connects, I don't know, a Pixar movie and your phone's GPS? Well, it's not magic, it is calculus. And today, we're going to use Steven Strogatz's amazing book, Infinite Powers, as our guide. We're going to demystify this incredible tool and see how it, quite literally, reveals the secrets of the universe.
All right, just think about this for a second. You've got these stunning animated films, you've got the satellite navigation that gets you home, and you have medical imaging that lets doctors see right inside the human body. I mean, these are three modern marvels that seem totally, completely unrelated. But are they? What in the world could they possibly have in common?
Well, you probably guessed it by now. The answer is calculus. It is the secret ingredient, the invisible engine that's running behind the scenes of so many things we absolutely rely on every single day. And that is really the key here. See, calculus isn't just another subject in math class, it is a whole new way of thinking. It's the language that lets us describe and ultimately understand a world that is always in motion, always changing. You know, Galileo figured this out centuries ago. He said nature is a book written in the language of math. And if that's true, then you can think of calculus as its most fluent, most expressive dialect, the part that lets us read all the really interesting passages about motion and change and curves. So, how does this language actually work? Well, it all pretty much boils down to one single, fantastically powerful idea, which Strogatz calls the infinity principle. And honestly, this is the absolute core of calculus. Okay, so here's the trick. If you have a really complex problem, like a curving shape or a speed that's always changing, you just break it down. You slice it up into an infinite number of incredibly simple, easy-to-handle little pieces. Then you solve the simple pieces and just add all those infinite results back together. It's the ultimate strategy of divide and conquer. This classic example, and this goes all the way back to Archimedes, it makes the whole idea click. So how do you find the area of a circle? It's a tricky problem, right? But watch this. If you slice it up like a pizza into more and more wedges and then rearrange them, the shape gets closer and closer to a simple rectangle. And at the limit, with an infinite number of slices, it actually becomes a perfect rectangle. And just like that, a hard problem becomes an easy one. That is the infinity principle right there in action. So with this powerful new principle in hand, thinkers could finally start to tackle one of the great mysteries of science, motion. I mean, how do you accurately describe something whose speed is constantly changing, like, say, an accelerating car or a planet zipping through its orbit? Well, you use the same trick. You just imagine that over an infinitely small moment in time, just for an instant, the car's speed isn't changing at all. It's constant. By breaking down a smooth acceleration into an infinite series of these tiny static moments, you can suddenly analyze it with incredible precision. And this brings us to the first of the two major tools of calculus, the derivative. The derivative is what lets you find that rate of change at one single solitary instant. A great way to think about it is like the speedometer in your car, but one that's infinitely precise, telling you your exact speed at this very nanosecond. Okay, so that's the first pillar of calculus. Now, if the derivative is all about breaking things down into tiny pieces, there has to be a way to put them all back together, right? Exactly. And the connection between these two ideas, well, it's one of the most powerful theorems in all of mathematics. And that tool is called the integral. The integral's job is to do the summing up part of our infinity principle. It takes all of those infinitely many, infinitesimally small pieces and adds them all back together to give you a total amount, like the total distance a car has traveled or the total area of that circle we were just talking about. So the thing you really need to remember is that they are perfect opposites. The derivative slices things up, the integral stitches them back together. The derivative asks, how fast is it changing right now? The integral asks, okay, how much has it all added up to? The discovery that these are just inverse operations, that's the fundamental theorem of calculus, and it's what completely unlocked its awesome power. So let's bring this all the way back to where we started. We have these amazing tools for breaking things down and adding them back up. How on earth does that connect to Pixar, GPS, and medicine? Well, in medicine, for example, equations that are built on derivatives, they're called differential equations, let researchers model the war happening inside a patient's body between the HIV virus and their immune system. By calculating the rate of change, they realized the virus was just reproducing at an unbelievable rate. And that led to the life-saving insight that a combination of drugs was the only way to fight it.
Or how about forensics? Using a specialized type of calculus called wavelet analysis, the FBI was able to compress its massive digital fingerprint files by a factor of over 20. Now, what that meant was sending crucial information over phone lines in minutes instead of hours, which completely revolutionized law enforcement.
And honestly, these examples are just the tip of the iceberg. The math behind CT scans uses integrals to build a 3D image from 2D slices. The smooth curves of your favorite Pixar characters are drawn with calculus. Designing jets, calculating orbits for GPS, even training AI models, every single one of them relies heavily on this language.
And this all brings us to this really profound thought from Einstein. The truly amazing thing isn't just that the universe has a language, but that we, through tools like calculus, can actually learn to read it and understand it.
Calculus gave us the language to read the poetry of motion and change. And it really makes you wonder, as we start to develop new mathematical languages, what other secrets of the universe are we on the verge of finally understanding?